There's just things in the way that you can't see out as far. Well, now when you have this telescope up there, you're going to be able to see through all that, like those nebulas and that gas, and it's going to let you see farther out into space. And so what that means is you're going to be able to see farther back in time, which is really cool.
Hello everyone and welcome back to another episode of Feeding Curiosity. I'm your host, Eric Wenzel, as always. Feeding Curiosity is a podcast that explores the precarity of human experience, and we challenge ourselves and others to think, question, and synthesize wherever our curiosity takes us. It is through conversations like what you're about to hear that we provide blueprints for others to learn and lead a more fulfilling life. And without further ado, let's introduce today's guest. Our guest today on the podcast is Bill Waterstreet, returning to the podcast as he wraps up his graduate degree from University of Michigan. Bill enlisted in the United States Marine Corps, starting his service in January 2011. When deployed to Afghanistan in 2013 and 2014, he assisted Army units in their information operation capacities. He completed his service in the Corps and was honorably discharged in January of 2015 at the rank of sergeant. Following his service, Bill began attending the University of Michigan in Ann Arbor in the fall of 2015. There, he majored in mechanical engineering and minored in electrical engineering. After graduating with his bachelor's degree, he continued on in Michigan and achieved his master's degrees in mechanical engineering with a focus on controls and completed the degree in April 2020. Today's conversation is a continuation of Bill's most recent chapter of his life, with the completion of his graduate degree and moving on to the working world. And as the title of this podcast, Bill will now be working with Northrop Grumman and its NASA partnership for the James Webb Space Telescope. Bill spends the majority of this podcast talking about his work on the project and a lot of the cool science that's going into the James Webb Space Telescope. And it's very, very cool for me to sit and hear another engineer talk about the things that they're working on, especially something like the James Webb that will be replacing the Hubble telescope. And in this conversation, Bill does a great job of making science accessible to the average listener. He really thinks of analogies and examples so that other people can understand who may not be as technical minded on how we test complex machines or how to test these very complicated projects so that they actually work when they go out in space and we actually can't fix them. And now for a short correction section before we get into the podcast, because we talked about the Big Bang and seeing things in space with some pretty intense numbers, but we really didn't fact check ourselves in the middle of the conversation because it would be difficult. I wanted to throw it in here now so that if you hear the numbers, just remember and make note that those numbers are off, and here are the correct ones now. So the first one being is the age of the universe is just under 13.8 billion years old, and the furthest observational limit of the Hubble telescope is 13.2 billion light years. Images are pretty unclear at that distance, and many more observations that are a little closer to that. The Hubble will be able to gather less than ideal images from objects 600 to 800 million years after the Big Bang at the furthest extent. The James Webb will be able to collect data from objects 200 to 400 million years after the Big Bang. And then a small correction of the actual James Webb, we said that each hexagonal mirror has only 3 grams of gold plating on its surface. We said 3 atoms thick. That might not be right. It's still a tiny amount with the amount of surface area, but it equates to 120 nanometer thickness of gold each. The planned operational life of the James Webb is 10 years. So I'm not sure what the exact year we said was, but we expect once it's up in space to be 10 years long. So that is all of the rap sheet here on this podcast. And I hope you all enjoy this fascinating conversation about Bill's next career working on the James Webb Space Telescope and his interest in space. Please enjoy.
Oh man, what do we want to get into? So we got.
Let's talk about the James Webb.
Okay, yeah. So
Yeah, we
I was
start
pulling
there
up
for
some stats just to make sure I get all the numbers fucking right here. But it's so.
What's the context first? For the...
Oh yeah. So I am people who didn't listen to me the first time. My name is Bill Waterstreet. I am a recent graduate of the University of Michigan. Just finished my second degree from Michigan. I have a master's degree in mechanical engineering with a focus in controls, mechatronics, so that kind of stuff. Basically, how your cruise control system works, how like things fly themselves, or way cooler, how to make like Terminators work. So
Robots.
Yeah.
Things.
Yeah, but it's any kind of control system. So like robot arms that build cars, like that's all controls how you move them. So anything that like kind of controls machinery and like the logic and algorithms to do that. And then also the physical knowledge and the electrical knowledge to kind of that's required behind that. So I'll be moving out to LA in 2 months to get a job, or to start my job with Northrop Grumman working on the James Webb Space Telescope, which is awesome. If anybody who's listening to this has not seen a picture, press pause and go Google it right now and take a look. It's got this awesome looking golden honeycomb mirror, and it's a beautiful thing. And I was lucky I was able to get a picture with it. I interned there down there last summer, and they extended me a job offer to come back. So that's what I'm going to be doing the next probably next 2 years of my life is till that thing launches. So desperately trying to not break it. So what it is, it's an infrared space telescope, and it's massive. It's the most technologically complicated thing we've ever launched into space, and it's the spiritual successor to the Hubble Space Telescope. It's an infrared light space telescope, so it means it doesn't see visible light like the Hubble does. It sees just a little bit further into the infrared, and it has let me see here. It has a near infrared camera, I believe a long infrared and 2 mid infrared. I could be getting that wrong though. And what these are going to be able to let us do while it's looking at infrared light is because the Hubble Space Telescope can only see out so far because there's gas and there's other light coming in, and it's difficult. There's just things in the way that you can't see out as far. Well, now when you have this telescope up there, you're going to be able to see through all that, like those nebulas and that gas, and it's going to let you see farther out into space. And so what that means is you're going to be able to see farther back in time, which is really cool. So the Hubble Space Telescope, I want to make sure I get this right. It's not on my fact sheet here. Okay, so I'm going from memory. These numbers might be a little off. So the Big Bang, I believe, was 14.1 billion years ago. Or maybe it was 13.1. Something like that.
It's one of those two.
Yeah. And then, so the Hubble is able to see, I think it's either 12.6 or 13.6, based on what I just said, billion light years outwards. So that's the furthest light away that it can see. And so that means, so I'm going to use this analogy because I used this with my aunt like a week ago, and I thought this up on the spot, and I was kind of proud of myself. So to explain, if this is confusing, why seeing farther away means you're seeing further back in time, imagine you are up on the International Space Station, and you are just looking out into the inky blackness of space. And I, with a big telescope, and like a pirate on like a ship, you're just standing on top of that thing. And I, 1 light year away, light a match, and you're looking at me in space. And it's a match that can burn in a vacuum. And so
it's a magical match.
I'm going to make sure I get my physics right, because if anybody should, it should be me. And so I light a match. What's going to happen then? Are you going to see it?
Oh, from the... No.
Eventually,
you'll
see it.
1 light year.
But so it's 1 light year away, so that light will take 1 year to travel from where I lit the match to where you are looking through your telescope. So that means, and if you look at something that's 10 light years away, you're seeing light of events that occurred 10 years ago. So if you are able to look further and further away, approaching 14.1 billion years, then you are seeing closer and closer to the Big Bang, to the start of the universe. And the James Webb gets us just a little bit closer to the origins of the universe than the Hubble Space Telescope. And that's why it's so cool. So, we're going to be able to learn things about the universe. Once that goes up and it's operational...
How far back is it going to be able to see?
So, I think it's... let's, for the sake of argument, it's 14.1 billion years old. The Hubble is 13.6. And then the James Webb is going to get to 13.7, I believe. 13.7 something.
I'm really curious to see what happens when we hit the point where we can see farther back in time than we suspect the universe is old.
So, okay, yeah, you can't. If the theory of the Big Bang is correct, you can't. Yeah. Because there is
nothing past that.
Well, so the reason we are distant from these things is because we all started at the same point. We all started at the same star. And the reason that these things are so far away is because we are moving away. We are moving away from the point in space where the Big Bang occurred. And other things are moving away in the opposite direction or in tangential directions. So like 90 degrees from us. Mm-hmm. And so really interesting thing about
that's the red shift.
Is, so things like that. You get shifts in color in the spectrum. But what's really cool thing is that, so they always theorized, they were like, okay, is the universe expanding or contracting? And so like, it was decades ago, they figured out, the universe is expanding. But then the thought for the longest time is that the universe is expanding, but it's slowing in its expansion or constant in its expansion, because that makes sense physically. You get shot out of a gun, the bullet's only going to keep its velocity, in a vacuum with no effects of gravity, or it gets slowed down by, like wind resistance or by gravity in this case in stellar bodies. So that was always the orthodoxy, the thought that like, okay, we're either continuing at the same pace or we're slowing down and everything will go out and come back in, and then the universe will reform into another giant solar body and we'll have another Big Bang billions of years in the future. What they found in the last couple of decades, and a couple people won Nobel Prizes for this, is the expansion of the universe is actually accelerating. Why? We have no idea.
Cool.
Yeah, and what that means is that there are things, so the expansion of the universe is getting faster and faster and faster. So we're not only moving away from bodies that are moving away from us. I'm using my hands when I'm saying this, so sorry to anybody who can't, but picture like two cars driving away from, two cars leave a McDonald's at the same time, and they're both driving in opposite directions.
This sounds like one of those early math problems I heard.
Yes, yeah.
Are you about to drop some fucking questions on me that I might be able to answer?
One's going 40 miles an hour. No! And so that's what we're, like, our solar system and then another solar system on the other side of the universe is doing. Well, what's going to happen eventually is that we're going to be moving away from each other so fast that we can no longer see them, because we'll be moving apart from each other faster than the speed of light. Now, neither of us will surpass the speed of light, right? But we will get to the point where they are so far away, and we are moving away from each other at such a speed where we can no longer view this thing. So there's an event horizon to what we can observe. From our solar system, and we already know that there are already things we cannot observe. We are moving apart so quickly, and they're so far away already. Yeah, so cool stuff. And so hopefully, so here's the other reason you'll never be able to see past the big. So that's the reason you cannot see anything further back than the Big Bang, because we were all part of that one gigantic singularity at one point. We all came from that, and so you can't, like, we coalesced from that, and the last moment of that's existence, the light that emanated from that, so like the moment the Big Bang went supernova, that has been accelerating, that has been moving away from the point of the Big Bang at the speed of light since the moment of the Big Bang. So you would have to get out to where that light is, which would require you surpassing the speed of light in order to see it. So if you could somehow surpass the speed of light, which we have no physical, like physicists are like, we're pretty sure you can't do it. It breaks all of our physical laws if the speed of light is not a universal speed limit. Now, there are possibilities. You'd have to talk to a theoretical physicist who is a PhD and expert in this field to really get into why or how much of this is possible. Like maybe wormholes are something that's able to so you take what's the movie? No, not Interstellar. The movie with they did the same thing in Interstellar, but they stole it from a movie in the 90s, which has the dude who played Lawrence Fishburne. He's in that movie. It's about a ship that goes out to Neptune or something.
It wasn't Event Horizon, was it?
It might be Event Horizon. Yeah, it might be Event Horizon. And they fold a piece of paper and stick a pencil through it. Yeah. So
space-time.
Yeah, so that might be a way you could get far enough out to see light from before the Big Bang. So, but Other than that, I don't think there's a way to do it, because you can't just put rockets on something and make it surpass the speed of light. So they thought for a second in the Big Hadron, on the Large Hadron Collider, that they had found some particles that were moving faster than the speed of light, but it turned out to be a sensor error. So yeah, whoops, oh my God, physics is broken. Oh no, sorry, our bad. Yeah. Basically,
wrong.
That was like science for like 2 months. So, yeah.
Freaking out.
Yeah.
Wow, that's so crazy.
Isn't there some theoretical show where they think they can make a black hole at the Large Hadron Collider?
So they were worried about that when they first started running it. They were worried they were going to smack particles into each other so hard that they were going to create a singularity. That hasn't happened. Yeah. So, and they're pretty sure it won't, but I don't know the science behind it. I just know that the scientists aren't concerned about it. So yeah, you'd have to.
I've seen the beginning of this movie.
Go prove it.
So yeah, just slam particles into each other and see what happens.
So what are some other?
It could never escape the lab. 10 minutes later.
So what are some other fun Big Bang? Oh, so okay, here's another fun thing about the Big Bang is that let's theorize maybe before the Big Bang, before this large, massive solar body that went supernova and created our universe as it is now. Was there a universe before that just all collapsed into this thing, and then then it reformed, heated all back up, and then shot it all back out? Is the universe cyclical? Is the question.
Yeah.
So it is impossible to know, because no information made it through the Big Bang. There is no information extant inside, nothing that could have existed before went into the stellar body that caused the Big Bang and remained when it, went supernova and kicked everything back out to make our universe today. There is all the information that existed before the Big Bang is gone. It no longer
It's totally
exists.
wiped and
Yeah.
then re-emerges and it's new.
So.
Wah, wah.
So yeah, anybody who wanted to, get closer to the, the origins of meaning in life through that method, sorry. So, turn to God. So, but yeah. So let's get back to the James Webb. So, working on that, it was originally scheduled to. I'm struggling to remember this date because everybody working on the project knew it wasn't going to happen. Because I think they were saying it was going to launch this summer or something like that, or maybe it was later in the fall or like late 2020, early 2021. Basically, everybody working on the project last summer was all like, yeah, it's not going to happen. So, so now they've delayed the launch again. It's supposed to launch in 2021. Summer-ish is kind of when people are feeling. So at this point, it's all put together. It's all, granted, remember, I haven't been down to the project for a year now, but I've been keeping up with it. It's all put together, which is a huge step that hadn't been done before. You have to, normally with a satellite, you'll do a whole bunch of tests to it to make sure everything's good. So you'll do a vibration test. You'll take it and put it on a vibration table, which is just a big platform that shakes and vibrates, and then make sure, okay, does anything fall off? They'll put it in these huge chambers, and then you'll cycle temperatures. So you'll go down, to the temperature of a vacuum of space, but then raise it back up to the temperature of launch. The temperature it'll experience during launch even a little more, and then the temperature the hot side will face, that's facing the sun, and to make sure it's going to be able to withstand all that. It's designed to do all these things, but you have to test it. And then they'll do a vacuum test, they'll suck all the air out, and then they'll cycle the temperatures too. So they basically run it through everything on Earth that we possibly can. We do this for, any important satellite we launch into space, we do this for. So any military satellite
Almost
that goes
any
up.
military product in general. That was my job. I did a lot of that stuff.
Yep. So they couldn't actually do it in California for one half of the James Webb Space Telescope. They had to ship it over to Texas because that was the only place in America that had a thermal vacuum chamber big enough to fit half of the James Webb in there and test it.
How big is this thing?
Oh, it's massive. So the main mirror is 6.5 meters across. Woo. So if I laid down, you could put 3 of me, maybe 3.5, head to toe, and that's just the main mirror. The sunshade.
24 feet.
Yeah, I'd have to do my metric to
3 times
feet.
3 times
converter. 6. Yeah. Oh yeah, because yards, meters. Yeah. So yeah, something like that. And so what was I going to say? Oh, so the sunshade. So basically the way it works is that the mirror needs to stay so extremely cold to be able to pick up the infrared light that's coming in from deep space. And in order to do that, so it's also very sensitive to interference from things around it, so it's not actually going to be in orbit. This is the other really cool thing about it, and extremely dangerous in terms of it working well. So it's not going to be in orbit around Earth when we send it up. It's going to be at the L2 Lagrange point. So if you imagine the sun, Earth, and a point in space in a line. So draw a line from the sun through Earth. Farther out, so I don't want to put a distance on it because I'm going to screw it up, but it's much farther than orbit. Way, way, way farther than like the Hubble is in orbit around Earth. So it's really far out there. So it's way farther than the moon. And so it's a point of stable gravity in Earth's orbit. So what the James Webb is actually orbiting the sun and not Earth. And so it's sitting out way beyond Earth. And so like as you can kind of picture like a compass being drawn in a circle. So when Earth is orbiting around the sun, extend your compass out and draw a bigger circle out there, and it's orbiting at the same rate. So, it's just always kind of like right behind Earth. And so it's very cold out there, and it's a stable point of gravity. So it'll always stay there, once we stick it there. And so to keep the mirror cold, you have these massive sunshades on the spacecraft part of the telescope. Now, what that does, and there's multiple layers, and there are these little, very, very thin plastics that are basically designed to absorb the radiation from the sun and dissipate it and stop it from getting to the main mirror, to the telescope part itself. And then there's like a cryo-cooling system on there as well that keeps it all super cold. And I can't remember the temperature differential, but it's hundreds of degrees like above, freezing on one side of the shades where the sun is constantly hitting, and on the other side it's like 4 degrees Kelvin. So yeah, which is insanely cold. It's near absolute zero. So it's like, I'm trying to think of a good way to describe that. So that's like colder than negative 170 degrees Celsius. So it's cold, insanely cold.
Fuck.
Yes.
Yeah.
And you need that for this to work properly. So cool, doing all this, awesome, right? Well, here's the problem. When we launched the Hubble, what happened?
Oh, did something get fucked? Was it one of the lenses?
So the main lens of the Hubble, when we sent it up, the outer edge of the mirror was machined imprecisely. How much do you guys think they were off? Like in a matter of like meters, millimeters, centimeters, etc.
I remember it being some absolutely insanely small portion.
It's like nanosmall. It's really small.
Some disgusting amount
It was
of
a
money.
couple of micrometers on the outer edge of the Hubble Space Telescope's mirror that they had machined it and were off by. I can't remember if it was too thin or too thick. And it screwed up everything. The thing was, you could get like blurry pictures of like the stars, but you couldn't get anything zoomed in from anything far away. And so it was, for its purpose, was nearly inoperable. Now, because the Hubble Space Telescope was in, I can't remember if it's low Earth orbit or geosynchronous orbit, but in orbit around Earth, you can get there at the time with a space shuttle now, and with a rocket. So that's what we did. We sent a space shuttle up, and we put some new technology on it. We didn't put a new lens. They just put some computational ability on there to correct for how the light was off because of the mirror, and it worked. And now the Hubble has exceeded its... we just had this anniversary. It's been up there, I think, for 3 decades working at this point. And its operational life was like a fraction of that. Yeah. And that's because, I used to know this. It was, I think it might have been 4 or 5 years, the operational life of the Hubble, but don't quote me on that one too. Now the James Webb, its operational life is 3 years. So all this work to get it up there and work 3 years. Now, you design and engineer the thing to be so robust that hopefully it goes up there and is able to function like the Hubble has for, a decade and a half or something like that. Now, here's the problem with putting something at the L2 Lagrange point, is that you can't really get a crew up there to fix it if something goes wrong. So when we launch this thing, it better work, or oops, there goes $12 billion.
Boy.
Yep.
Jesus.
How do you test for that?
So you run every electronic test that you can on it. You test everything. So like, let's say when I was leaving, when they do this big boom. So the mirror that you see when you look up the James Webb, and all this beautiful honeycomb structure, that's gold on those mirrors, by the way, which is super interesting. Everybody's like, oh my god, that must be so expensive to be painting this thing in gold. There's a reason that there's gold on the mirrors. Like, there's somebody, one of the physicists or something, not my department, knows why that's there. But, so the gold is actually 3 atoms thick.
Whoa.
On the James Webb's mirrors.
Atom level.
Atom level. The gold that is on that telescope is one of the cheapest things on the telescope. So,
Jeez, talk about thin paint, man.
yeah, 3 atoms thick. So there's this big main mirror, and what that does, that reflects the infrared light up to, you can see in renderings of this, there's a big boom that comes out in front of the mirror, and it reflects it up to that. There's another smaller mirror in there, and that directs the infrared light back down into a hole in the center, and that's where all of the infrared cameras are. So that big, beautiful mirror you see on it, that's all it is. It's a mirror directing light where we want it to go, to get to the cameras. And so one of the things they did to test things, like one of the big tests we did when I was leaving, is they tested the boom. And so, you have to simulate, using it in 0G. How do you do that? Because you can't just like stand it up straight and like extend the boom because you have gravity pushing down on it. So what you do is you turn it sideways, and then you extend the boom out, and it's as if you are extending it in 0G, because all the gravity is acting perpendicular to it. And like it's basically only pushing down on where it's pushing down tangentially, so perpendicularly to your axis of motion in, extending this boom. Because the boom extends, in 2 axes of, movement. And so if you put gravity in the 3rd axis, then it's not affecting that motion that you're testing. So that's one of the things you can do, and then you run every electrical test you could possibly imagine.
So the boom, the by turning it inside, you're mimicking Earth's or the gravity that it's experiencing. What is it exactly that's allowing for the sideways motion to take the place of gravity that's acting on Earth?
So you are taking gravity and you are pointing it in a direction that does not affect the motion you're doing. So I'm trying to think of a good analogy.
Would there be?
I'm gonna come up with something really clever here.
All right.
Okay.
I'll hold my breath.
I want you to take your arm and stick it out in front of you, palm vertically. So make like a knife hand, And now do like the so like move it like that, Yeah. Now you can feel the change in gravity because when it's like when your hand is pointing straight up. You feel the force you need to move your arm is different than when it's straight out in front of you. You need more force.
Right, it's like doing dumbbell flies.
Sure.
Most of the pressure is up where you're at your highest point.
Now, same knife hand, turn it horizontally. And now move it in that plane. So from your chest back out. You see how the force you need to move your arm here is exactly the same. It does not change depending on gravity. And so that is mimicking, so in this 2-axis plane, so the horizontal plane as you see it sitting in your chair, gravity is having no effect on motion in this plane.
It's the consistency of the gravity.
Yeah, and now you are mimicking 0G. They're doing
Got it.
So, yeah.
That was such a quick analogy that you came up with.
Yeah. I'm pretty proud of that one too.
We all
are. So let's see, what other cool stuff? So, yeah, it's going to go out to the L2. Basically has to work. We could fix it. Like, you can get a rocket out there and back if it didn't work and, Elon wanted to launch, a Falcon Heavy at it, with a crew. We could fix it, but it would be absurdly expensive to do. Yeah. So, yeah. Oh, points of failure. Okay.
Where can we fuck this up?
Yeah, let's talk about how easy this is to fuck up.
And how many people are losing sleep over this?
Your average, your really complex space telescopes and satellites that we've sent into orbit have somewhere in the range of between 50 and 70 to 80 on the high end single points of failure. So single point of failure being if this one thing goes wrong, the whole fucking thing doesn't work. So the James Webb has 170 some.
Oh boy.
So more than double the most complex thing we've sent up before. So, and if one of them goes wrong, and there are things you can do depending on what it is and when in the deployment cycle, because this thing's a transformer. It's all packed into the cone of a rocket. at the tip, and when you launch it up there and get it, like going out there, once it's approaching the L2 Lagrange point, it starts unfolding and doing a bunch of stuff folds out and things deploy. And if you can get like your first solar panel extended out properly, like, okay, cool, like let's say like then the battery fails like a couple hours after that. Well, it doesn't matter, we have the solar panel out. We don't have as much power as we wanted, but like, we can take our time and slowly unfold things.
There's ways to
mitigate
some things, yes, but there are 174, I might be around about the 170 some single points of failure. So things that if they break one thing, it's all fucked. So, yeah. And then
tight.
Yeah. So yeah, my job is to basically finish putting it together. It's almost entirely put together at this point, and test it, and if everything's wrong, fix it. So before it goes up. So yeah, that's what we're working on. So, and I don't want to get too much into like details because I don't know, the company might not be happy. Like if I'm detailing like, oh, this went right and this went wrong.
Right.
So,
what are the access codes to the place where you're building this?
Yeah, exactly. Well, so here's the really fun thing about it is because like Northrop Grumman has a lot of classified projects that they do for the military. This is a NASA project. All NASA projects are totally unclassified, as far as I know.
Besides the alien shit.
Yeah, you're not supposed to tell them. I told you that.
Oh no.
I need to make a call.
Uh-oh. Now we're gonna have the UFO people.
So working, there's actually an observation deck. The James Webb is in this big warehouse in LA. And so that's where I'll be working, and in this massive it's a massive clean room. So it's like one of the biggest like bays you've ever seen to like build something, massive room. And it's all a clean room. So it's in like, anytime you go in there, you have to like, you go through, you're cleaning up, you clean off your shoes, you put little, those things that cops wear, they're
booties.
Little booties, and you put on a whole clean suit, you put on a mask, you're just basically from head to toe, you cover up all your hair, everything, your, like gloves, everything, if you're going to come up to the satellite, you even tape your gloves on, so nothing can like fall out of your sleeves. And you're also the gowns you wear, so they're hyper clean. They're made of material that's very like easy to 100% clean. Like there's no fibers that are going to come off them or anything. They're also what's the name for it? Shit. It's where if you're standing inside a metal cage and somebody like tries to zap you with 1,000 volts, it can't.
What's it? ESD proof?
Yeah, ESD proof. So electrostatic discharge proof, but there's a name for it. It's a something cage.
Faraday cage?
Faraday cage. Yes, that's what I was looking for. So it's they're also a Faraday cage, and that's really important because static electricity is one of the biggest things that can harm a satellite. So they're a Faraday cage. So any electricity that comes and like touches you, they will like run through the suit and hopefully ground itself. And so you aren't going to go bring static electricity to the satellite. Now what you also do, we have these little like metal lines that run all across the satellite, and so you wear a wristband. It's a metal wristband connected to like just a little alligator clips. And so you always have that on, and anytime you get within 3 feet of the satellite or the spacecraft like it's attached to or anything, you come up and you clip onto one of those metal hooks. So even if you generate a static charge, it just goes straight into this thing on your wrist. The static charge that your body built up goes right through the wire into this metal cable that's like near the satellite and takes it into the wall and gets rid of it.
Cool.
Because static electricity is one of the biggest threats to satellites, because when you touch something, the static shock can jump into the electronics, and like really small transistors or anything, that really small metal bridges between components, it can, if your static charge shock is a high enough voltage, it can like totally short out those it can totally break the link in those components. So it can like delete a piece of metal, like burn it away between two components, and you've lost that connection, and maybe your thing doesn't work now. That's even worse. What it can do is it could be strong enough to where it destroys most of that bridge, but it still works in testing because you have a little bit of metal left. But then you launch it, and 6 months down the line, that last little bit burns off, and now it doesn't work. So that's why static electricity is you have to be so careful for it when you're trying to build this thing.
That's remarkably complicated.
Insanely. And so easy to break. So
that's that 3 atoms for you. That's why it's part of it so sensitive.
Every little thing.
Every little thing. But the nice thing is, so in this clean room that we work, there's an observation bay. And if like somebody from the company, like it's not even on your project, you just come in, you log in on this little logbook and you bring anybody in. Wow. And show them the project. So I showed a couple of our buddies. So was it Connor and his buddy came down, So
That's
they were
cool.
visiting. Yeah, I was able to take them up there and like and they have like a little video screen in there that's playing facts about it. And there's a bunch of facts on the wall. And I can tell them all about it. So yeah,
This is the James Webb.
yeah. That's how I got my practice for this. So showing some
yeah.
friends in there.
As
So,
like a tour guide for
Yeah.
our homies.
yeah. So. But that's cool because I can also talk about it too. You're not working on something classified. I can be like, oh, so this is what I do all day. It's so cool.
That's really cool.
So, but no, what I do all day is mostly because I'm not always down in the clean room. A lot of times I'm upstairs from that, just at a computer, and anything you do to the James Webb is hyper detailed and logged. Everything. If you turn a screw, there is a sheet of paper that logs exactly what screw you turned and like how far and everything, every little detail. And so my job is to, okay, hey, like we decide we need to do this to the satellite. Cool. I then need to like write a step-by-step procedure of the way we're going to do this down to the smallest detail, and then it goes through a whole approval process, and I'm not very good at it yet. So I'll bring it to a more senior test engineer. He'll look it over and be like, okay, you got all this stuff right, you got all this stuff wrong, do it this way. Cool. A couple drafts later, then you push it out to all the different departments that need to look at it. So okay, electrical guy over here, a mechanical designer over here, some somebody higher up the project manager, a technician here, and they'll look at it and be like, change this, change that, And then you get to the point, after like a week of working on this, you go, okay, cool, ready to run it. And so then you take this down to the floor, and you have like a couple of guys, with you, because I'm actually not allowed to even touch the satellite. The guys who will really turn all the wrenches on it are technicians who have been specifically trained. That's all they do is they do the physical work to this. And I'm sitting there telling them this is what we need to do, and they're super well trained. So if I fuck something up in I told you to turn it with this tool, and they're like, no, you actually don't use that tool, use this tool. I'm like, okay, cool. And you have to go and detail I was wrong in saying this, and we're actually using this tool, and put an addendum on there.
Interesting.
Yeah, and so but literally everything that's done to it is documented, and so that's a lot of the job too, is just writing down okay, this is what we're doing. So and it's if you want to feel how my job is, try to go and write down a step-by-step instruction sheet of how to make yourself and then eat a bowl of cereal. So just from as detailed as you can possibly be.
No detail unturned.
Mm-hmm. And then take it and then go to a friend and say, I want you to follow these instructions down to the letter. And then see how it goes. Because parents will do this with their kids all the time.
I'm picturing how our friends would do that, and it would be a mess. They would intentionally make that worse.
Yeah. I did that in college. We had a PB&Js, but
yeah,
that's a common one.
It's hilarious because it's crazy what people will
It's a lot of
do.
inference.
Yeah, it's okay, apply peanut butter to sandwich. Okay, take your hand, stick it in the peanut butter, and smear it on the sandwich.
You take it as literal as possible.
Yeah, and so that's basically what I have to watch out for is what things are worth denoting and caring about and what are not. What can be inferred and what can't. So yeah. So yeah, that was a lot of me talking about the James Webb. But yeah. Any questions?
That's so cool.
Yeah.
Well, can you give us a tour? We're moving to LA.
Yeah. If you're in LA, I can give you a tour. Yeah.
Oh, dude,
So.
we're doing that.
It's I'm in.
Yeah, I'll be moving down there late August, so end August. So.
Oh,
Wow,
still.
that's
August
ironic.
21st.
Same time.
Yeah, good stuff.
Awesome.
Yeah.
So cool.
Yeah.
It's hot in here.
Dude, it's
hot in here. So.
It's
yeah,
hot.
we're just hot boxing it in here recording
Yeah.
this podcast. We just
90
sweat.
degrees in here.
So.
And just
Yeah, so we had to kill the AC, so the audio was all right.
yeah,
so.
not full of noise.
the sacrifices we make.
I know.
Oh yeah. So you're welcome, random listener.
Audio, and they can learn all about space. It's actually funny you brought this up because I just finished reading the book, The Cuckoo's Egg, the book by Clifford Stoll, astronomer turned website or cybersecurity expert. Accidentally, he was one of the first documented cases of basically break-in via networks. And so he basically talked about how you can't, if in astronomy, if you don't write it down, it never happened. And that's exactly like what you're saying. It's you just keep a logbook of everything you do. And it's really similar to what I did as my job when I was doing testing. It's everything you do, you write it down. You have to have a paper trail. Otherwise, people say, well, it might as well never have happened.
Yep.
So it's the attention to detail.
It sounds so tedious.
It very much is. Science is tedious
my
work.
mind,
Yeah,
dude.
it worked. I really enjoy it though, because attention to detail is something I'm really good at. So.
Reh.
Right. So we were talking about before. My roommate, he's actually the one who got me. Him and another buddy, where they worked for Northrop Grumman on different projects previous summers, and this last summer, so a year ago, they were like, hey, you should, let's get you out here, working for them. And it took me a couple times. I didn't get an interview until I took my third swing at it, and then I finally got through the, it wasn't even a person, it was just the internet wall.
The automated whatever.
Yeah, trying to get through. And I finally did, and I got a nice interview. And it was fun. I don't think I've ever done a real interview for a job, which is really interesting. So I'm at 29. I'm working on a space telescope, and I did one, but it was over the phone with 6 people on the other end. And it wasn't they weren't really testing me that much. It was very laid back. I cracked a joke. There was a ex-Marine in there too. And he asked me at one point, he was like, hey, because we were talking about my service and stuff, and he was like, oh, okay, what boot camp did you go to? And I was like, oh, Parris Island, where real Marines come from. So, and then everybody laughed, and once you get a room of interviewers laughing, I was like, oh, well, I got the job. So. Yeah. And other jobs I've had have just they've been situations have been it's been a family company, or it's been just the military or another thing where it wasn't a real interview, there was not too much pressure. So, because I've had buddies who went to go work for SpaceX, and they're like, yeah, I did how many rounds did Kenny do? It was
some ridiculous.
It was 9 or 11 fucking rounds of interviews.
Yeah, and they would
leave. Ridiculous.
Yeah, and they'd take him and they'd be like, okay, so here's a whiteboard, here's the problem, figure it out.
Yeah, and they'd test him
just live, everybody's sitting in the room watching him try to solve this insanely complicated physics problem. It's just
Throw to the deep end.
Yeah, he ended up working there as a professional welder because he did welding.
It was a special kind of welding. It was arc welding or something. I can't remember. Maybe that's correct. Maybe it's not. But yeah. So yeah.
Yeah, which was a weird combination of his engineering background, right? What was his background?
He's mechanical.
Mechanical. Yeah. Mechanical engineering background mixed with some
aerospace. He's aerospace. Yes.
Aerospace.
I'm sure about that now.
It makes sense. Yeah, it would make sense that he would do aero if he was going to.
Yeah.
So aero plus the fact that he did some welding stuff when he was in the military.
Yeah. Got it, yeah.
He was also I think he wasn't too much of a fan of SoCal. So
yeah, I mean he didn't stay there for very long.
No, he was there a couple of years.
Brutal on their
phone. Yeah, SpaceX really runs their people hard. But it follows the same cycle of the way employees are. If you're being polite, you could say used, or impolite, you could say abused in many startups. So Apple went through the same phase, Google the same phase. You have when the company's very young, very hungry, really trying to make it. They'll get young talent in there and they'll run them 70, 80 hours a week. Just work. If you can't keep up, go, because there's somebody else waiting to take your place.
Yeah.
And then as they get more established, they'll start to draw that back and become so now with great, we can talk about SpaceX. So now with the launch of the Dragon capsule and the first launch of an American astronaut from American soil in almost a decade, now we're starting to see SpaceX hit that point where they are well known and documented as a major player in the aerospace industry. They're no longer just hungry, gimme. Now I'm sure they're still going to work super hard. It wouldn't surprise me if they still have people working 50, 60 hours a week. But a little bit of the pace, I would not surprise me he slacks off some. And I mean it's also based on the project too. If your shit's near launch, then all you're doing is working. That's literally your job is to be on call 24/7. You're always working, getting this thing ready to go.
Right.
But
and there's a benefit there for the employee too, right? It's SpaceX is a name.
Yeah.
Right. And you may go there and you may only work there for a year, and it may be horrible, but now you've got a year's worth of work at SpaceX. Talk about a
resume booster.
It's it really is trial by fire.
Yeah.
And then once you've been honed in that way, then you go to any other company that's way more relaxed and you'll be a champ.
Yeah.
It's
forget it, right? It's a crucible. It's you go in there, you get bent into shape, and then you go anywhere else. And
it's the boot camp for engineering.
Yeah, really.
So why the Dragon capsule is so cool? What they just did is so awesome. Is they've been able to take the amount of money it costs to launch an astronaut into space and knock that down ridiculously well. So I think it's
I forget the number.
I think it's $60 million per astronaut to launch somebody into space. Now, what Boeing, because it was a dual contract between SpaceX and Boeing. They were both designing systems to launch privately owned systems to launch astronauts into space from the U.S. And so the Boeing system came in somewhere around like 105 million per astronaut or something, which is about what we were paying the Russians to launch our astronauts into space off of their rockets.
Huh.
SpaceX is doing it for 60. So yeah, and they're like what it costs them per astronaut to launch, to do a launch as well is, I want to say it's like 30. I can't remember if it's per astronaut or just period. But like if they're able to recover the booster from the rocket, so if anybody who doesn't know, so the SpaceX rocket boosters, they fire and they go off into space, and then at some point the first stage detaches, but it saves enough fuel, and then like drag fins deploy, and it plummets back to Earth, exactly to where they have a platform sitting out in the sea, and then right at the end the rocket fires and it lands itself. And then you can recover that booster, refurbish it, slap it back on a new rocket, and fire it again. So if they're able to do that, I think it's like their cost per launch is like, I can't remember if it's per astronaut or per launch, but it's like 35 million or something like that. So yeah,
that's awesome.
Yeah, it's
efficiency at its finest.
Yeah, it's really cool.
Isn't Virgin Galactic? Is that a legitimate competitor, or these feel like
this Virgin Galactic,
like the Kroger brand? You know,
Virgin Galactic and
Blue Origin. Blue Origin is Jeff Bezos.
Yeah, so they're doing something different. They're trying to do a commercial space flight. So they're basically just trying to get
like a tourist type.
Yeah, well, they're trying to get a craft together that can get tourists into a low Earth orbit that's going to, you just go up and it decays real quick and you come right back down. So like, whereas the SpaceX rockets are like, these are like the rockets NASA used to turn to like JPL, Jet Propulsion Labs, and like be like, oh hey, build us a rocket that can get us to orbit or get us to the moon or something. Right. SpaceX is building rockets to go beyond a low Earth orbit for tourist purposes, whereas Virgin Galactic and Blue Origin, as far as I understand it, are just trying to get to this low Earth orbit that's a little more easy to achieve.
So it's a different market.
Yeah. So I encourage anybody who's interested in this stuff to just hop on YouTube. There's a million really cool videos out there that have their facts way more straight than I do on this stuff and are really entertaining to watch. And so go check it out.
Yeah.
So, yeah.
SpaceX live streamed all the launch for the Dragon capsule, so if you can go watch all of that stuff.
And you can. It's a beautiful thing. So I watched it live.
Was that when they landed the two in synchrony?
No, that was last year.
Yeah.
Those are the 2018.
Those are the Falcon Heavy boosters.
Yeah.
So, yeah.
That shit was cool.
Yeah.
They did all that too, and then with the most recent one, they showed the inside of the cockpit with the astronauts.
Yeah. So that was actually one of my last projects in school, was to take care. There's a smaller company, I think it's a Rocketdyne something or other. They have I'm trying to remember the name of the rocket, and it's not coming. It's like a X, but it makes a Z sound, so I don't know, like this is a Celsior or something like that. So, yeah. Xerox, like that kind of shit. But so they make little tiny rockets, but they can hover. So you fire it, and the control system on it is able to make it launch and then just hover right there, like a couple feet off the ground. And it's a rocket, so it's firing, but it's just hovering right there, and you can direct it to move around a little bit. So that was one of my last cool serious project for school, was we basically tried to get that to work, design a control system that could do that. That was hard. So yeah, that was a little more difficult than I expected.
Couldn't imagine.
Yeah, I know, right? Crazy. So we were also
step up.
We were trying to adapt a model of a plane, or we were trying to adapt a model of a cruise missile from some papers we found. But a cruise missile flies horizontally and then just turn it vertically, and that actually turned out to be insanely difficult to do, just by the way you transfer axes and the way the forces move and everything, and how easy it is to fuck things up, and your cosines and your sines and what angles where. And yeah, so and then it's, you have to transfer between your different coordinate frames, so the missile rocket coordinate frame and your Earth coordinate frame, and then so that ended up being tough. So yeah, a little difficult, but we did it. We got it to work sort of on paper, maybe a little bit. So why what the SpaceX rockets can do is so cool is because they're not throttling that much. They can't throttle how much force they're putting out of the bottom.
It's just
that
open
much.
Or closed, more or less.
Mostly, you can throttle it a little bit, but not. It's it's 80% or 100% or something like that. So it's not like a helicopter where you can we're coming in to land, cut it, and we're landed. No, you need to. So what they'll do is they fire their solid rocket booster up until an exact amount of fuel, and it lets go, and it comes back down to Earth, and then when it's coming down to land, they're firing it again right at the end when it's coming to land itself back on their sea platform. it's running out of fuel, almost like right there at the like they're not there. Imagine trying to do that without being able to throttle, like how much force you're putting out. So you have to fire this thing for exactly the right period of time.
Right. So
in order
So
to
it just
runs
touches
out.
down perfect. Just,
yeah. So I think they do have like they can shut off like they can shut off like the when it's firing. So if they have a little bit of fuel left over, that's fine. But like they have to fire the exact amount, and they can't like so it's like okay, we have to if we want to decelerate from this speed to this speed, we have to fire it exactly for this many seconds. And if you're a little bit off, then it's gonna hop and fucking fall over and explode. So or it's gonna land too hard, fall over and explode. So which happened a couple times. So, but
Also great videos.
yes, also
still
fun.
just as entertaining.
Yeah,
Oh,
going
yeah.
up. So, but yeah, space stuff. So,
Yeah.
Cool.
Yeah.
Damn.
Any other questions or thoughts? Because this is something that I really wanted to talk about, but because of other things going on in the world, it hasn't been gotten to talk about SpaceX and space launching.
Yeah.
You're the man to fucking ask to some degree. I mean, whoever, but like the tech.
I know this
I
stuff,
don't,
so I'm just
yeah.
I'm just curious for the non-technical people.
Yeah, I guess non-technical question. And apologies on the last podcast you explained this, but how'd you fall into all of this?
Oh, so I worked in just a local company that did like controls engineering sort of stuff, some engineering projects. So I was working mainly on like these house-sized test systems for helicopter transmissions. So you like take a transmission for a Black Hawk, and so a lot of people, if you don't know, a helicopter is a lot of it, like a lot of the components is all a transmission system. So like so like you have an engine, you have jet engines on the side, like you see usually up on top, to like either side. And while that's running, it's just basically taking that turbine momentum and translating it into rotor momentum exactly the way you want. So the transition like systems on these things are immense and usually like one of the first things to break. And so you have these huge test systems. You just take this, massive transmission, for a helicopter, and you plug it into this machine that's the size of the house, and you hook everything up and you run it. And it spins it at, 10,000 RPM or, 5,000 or whatever you want to run it at. So I was working on those for a couple summers, and like that was interesting. I really enjoyed it. It was with a company called Red Viking. And they do a whole bunch of other really cool stuff. But so yeah, that was fun. But then I was like, okay, I want to get out and do something a little bit different. And so I fell into Northrop Grumman due to my friends. So my roommate and another so the three of us, all ex-Marines, who are here doing engineering at Michigan. And they had worked for Northrop Grumman, and they had good things to say. And like they said, the company culture was great, and they're working on really cool projects. And so like good company culture is like really important to find in engineering. So. And so, yeah, they're like, hey, take a look. And so I did. And in terms of how I got on the James Webb after I interviewed with Northrop, luck. So, yep, I signed up for my first internship with them. I was like, yeah, sure, I'll come out for the summer. I'll work on, like, what do you got, down at Space Park. And they threw me on the James Webb, and it was just luck of the draw.
Dang.
So,
That's
yeah.
so cool.
Yeah.
It's so neat.
That's awesome.
Yeah. So, and then, so my roommate, who's down in, he's on his way down to California right now, he's also working on the James Webb. He was working on a different project. I don't know if I'm allowed to say what it was, so I'm just gonna not.
Yeah.
Yeah.
We don't want to
But
infringe on
he was
NDA
working
stuff.
on something else, and it's an early stage project, and he felt like he wasn't really being utilized. Like he wasn't doing much hands-on stuff. He didn't feel like he was really being utilized too well, and so I was able, when I left my internship, because he was working a 6-month co-op, to get him moved over to the James Webb. And so me and him, we've lived together here at Michigan for the last 3 years. Now we're moving down to LA together. We're going to be working on the James
That's
Webb
so
together.
legit.
And, yeah, so living in Cali, riding our motorcycles together. So, yeah.
Awesome.
So, yeah.
Cool. Well, I mean, I think we're almost at an hour right now, so if there's anything else you wanted to throw
Well,
in
I'm down to talk about like a ton of like whatever you want. So I don't know how long you.
It's up to you guys because it's fucking hot in here. So
Yeah, it's whatever,
if
like
we
however
want-
long you guys
If
want
we
to
want
go.
to keep going,
So.
we totally can. If
Yeah.
not, we can.
Because like
I'm
I'm perfectly happy to jump into some of the conversations Joe and I have had.
Oh, sweet
Over
Jesus,
some
we'll be here
time.
for hours.
Yeah, I
and
know,
hours
right?
now.
So,
we can continue those off air if we want for now. and
yeah,
then-
so it's. I mean, we can. Yeah,
can always
we can
pick
cut
it
it if
back
we
up at
want,
some
or we
point.
can. Yeah, whatever we want to do. So
We can always do another.
Yeah.
yeah,
All right.
cool.
We'll cut it for now because we'll keep this on all
That was
things
also
being space.
yeah, that was very space themed.
Yeah, which
themed,
is totally
too,
cool
so.
with me. Yeah.